let's look at the situation now with three variables. So, we have two equations again, and think about what the graphs of these are, right? These are both the equations of a plane. So think about, we talked about the different situations that could happen. Think about what those possibilities are. And let's look at what we get here. So, just like before, I'm going to solve this in the exact same way. All right? So we got 1 and 2 again. And when we're solving these, our goal is going to be to try to eliminate variables as best we can. All right? When we solve systems of equations, we want to eliminate variables so we can try and solve for them. Now here, we have two equations and three variables. So we sort of have too few equations going on. So we'll see what that ends up giving us. All right. So the easiest one here to get rid of would be either x or z. We could get rid of the y's as well, but let's do the z's since they have opposite signs. All right. So here, this is a single negative z. This is 2z. So if we do 2 times equation 1 plus equation 2, right? 2 times equation 1, that's 6x, plus 4y, minus 2z, equals 7. And then x minus 3y plus 2z equals 0. Okay? So, do this. These cancel. And here we get 7x plus y equals 7. Alright, so now we have this equation, and this is as far back as we can actually go. So, what do we do here? How do we proceed? Well, when we get an equation like this left over, and there's no other equation to work with here, we know that we're going to have infinitely many solutions because this equation can be true. So, infinitely many. So, how do we find the answer? Well, we're going to have to do the same thing we did before. All right? So, let me call this thing here equation A, let's say. Okay? So, what we're going to do is we're going to set... We need to, again, pick a variable and set it to be one of our parameters. And we should use something from this equation here. All right? Now, there's no rule for which one you need to set as your parameter, but think about which variable is easier to solve for. So y is really easy to solve for, which means we should make x our parameter. So we're going to set x equal to t. Okay? Then, equation A gives that y equals 7 minus 7x, but x is t. So 7 minus 7t. So now we know what x is and we know what y is. How do we get z? Okay, well, to get z, we just got to plug all this stuff back into equation 1 or 2, right? Anywhere where we can solve for z. I would use equation 1 here since it's easier to solve for z. Just like we, made x the parameter because y was easy to solve for. Right, so equation 1 gives that z. Okay, let's solve for z. This is going to be 3x plus 2y minus 7. Right, if we just solve this for z. And now we just plug in x and y. So we get 3t plus 2 times 7 minus 7t minus 7. And then we simplify this. This is going to be, let's see, 7 minus 11t. Is that right? Yep, okay. Alright, so now we have our x, y, and our z in terms of the parameter t. So the solution is going to be x, y, z equals t, comma, 7 minus 7t comma 7 minus 11t. Right? And again, it's a good idea to understand what this solution should look like. So we're going to separate out the constant and parameter terms. So the constant term is 0.77 plus t times the parameter terms, so 1 minus 7 minus 11. And there's our solution. And again, think about what kind of object the graph of this is. Right? If we have these two planes, how could this system work out? Well, this right here is the equation of a line. And if we think about it, if two planes intersect, they're going to intersect in a line. So this should make sense for the situation here. So if we plot the graphs of those two planes, right? Again, the blue is the first equation, the orange is the second one. Not that it matters so much here. We can see they're intersecting in this line right here. Now it's going to be a bit harder to work out, exactly the directions this time. Should be something like this. Right, so there's our line. But again, the exact position of that line is not important. The point is that they intersect in a line. All right? So think about what are the other situations, the other types of intersections we could have with planes. Well, one that we could have is something like this. What do you think this situation is? Right, I've graphed both of them here. What do you think is going on here? Well, you might have guessed, like before, with the lines, this is a situation where we have the two planes being identical. So let's see what happens if we try to solve that. Right, so that system of equations is 2x minus y plus 3z equals 4, and 8x minus 4y plus 12z equals 16. All right, so I'll sort of spare the work. I'll let you kind of check this out. But if we did 4 times equation 1 minus equation 2, we're going to get 0 equals 0. All right? I'll let you verify that on your own. So what does that mean in terms of writing down the solution of this? Right? This is the interesting part. Because now we have essentially 3 variables and just one equation, because these two are the same equation, so there's no new information. What do you think we would have to do? So, when the solution was a line, we had a point plus the direction of the line. Right? The solution now is an entire plane. Think about how many directions there are in a plane. There's 2 directions. So, since we have sort of 2 directions of freedom to move in on a plane, we should have 2 parameters. All right? So let's look at that situation here. Or how do we solve this? All right? So basically all we have is this equation. All right? Equals 4. All right? We only have this. We have to pick 2 parameters now. And again, just like before, we can pick any of the 3 variables, or any 2 of the 3 variables to be our parameter here. Which one do we pick? Well, what variable here is the easiest to solve for? That should be y. So we're going to pick x and z to be our parameters. What we're going to do is set x equal to t, right? And z equal to, let's call this s. Okay? Then we get that y let me just make that line a bit shorter. All right, then we get y equals 2x plus 3z minus 4. I almost wrote equals 4. Minus 4, right? Well, plug in the t and the s, and we get 2t plus 3s minus 4. I know it can seem a bit silly that we're just swapping x for t and z for s. It seems a bit silly, but it has its purpose here, right? We're trying to set up parameters. We're trying to move away from this Cartesian equation here, right? So what is the solution? Well, the solution is exactly the same as what we've been doing. T, comma, the stuff for for y, so 2t plus 3s minus 4, and s. Now the difference this time is there's 2 parameters. So what we're going to do is split it up into 3 pieces. The constant piece, again, which here, the first one has no constant term, the second one has -4, the third one has none. And then one with the t's, so say t, 2t and 0, plus 0, 3s, and s. Now, of course, just like the last one, we're going to factor out these parameters. And so the preferred way to write this is like this, right? Factor out the t, so we get 1, 2, 0, plus s times 0, 3, 1. Right? So what does this do? Let me bring back up the graph of the plane here. What this does for us here is let me make this a little bit bigger too. All right, what this kind of does is say, all right, well, you have some point on the plane, which is this one right here. Right, here's our point on the plane. And it's saying from this point, we have 2 independent directions that we can move. One of them is in the 1, 2, 0 direction, which, I don't know, might be this way. And the other one is in the 0, 3, 1 direction, which is probably the kind of upward one. So you have this direction and this direction. Right? And hopefully that makes sense. We're allowed to move in some combination of those 2 directions. Right? So, again, I want you to kind of be able to associate the equation we get, the algebraic solution, with the graphical solution, the geometric solution. All right?